Welcome again. It is Dr. Wood, and we're talking about parametric versus non-parametric statistics. So when we talk about a normally distributed set of data, this is what we're referring to, is this nice bell-shaped curve, this nice Gaussian distribution. Remember, you're typically going to see this when you have a truly random sample being pulled from a general population, right? Because values tend to regress towards the mean. You're going to find that the mean, because it is average, is going to be the most common value you're typically going to be picking up on. Remember that as you get to more and more extreme values, they should become less and less common because, again, outliers tend to cancel each other out and people tend to regress back towards the mean, right? This is how we come up typically with normal values for labs and things like that. Now, again, as I mentioned, the truly random data should center around this. Very frequently, though, you're not going to be able to get that truly random sample set, right, due to a number of issues, including costs, including study design, a lot of other issues there, right? And again, just because I say that it is a normal distribution does not mean this is normal, right? I could be looking at something like, blood pressure in patients who are obese with metabolic syndrome. They're going to skew higher than what a normal, quote-unquote, healthy kind of person would be. It just means it is normally distributed, meaning that you don't have a ton of outliers that are skewing the data one way or the other. Again, it's really kind of centering around this mean here. Now, again, how do we know if we have a normally distributed set of data? Well, typically we're going to have tests for normality, right? It's going to be looking for things like outliers, and it's really trying to compare and see, like, well, taking this data, how does it stack up against what the general population should be? Maybe difficult to know that information, but if it looks like your data set is significantly different, right? If they're statistically significantly different, it means that it's very unlikely that if you found a data set that has those values, it's unlikely to be due to chance alone. There's probably something that's different between your sample set versus the general population. Again, if you're looking at a research article that may not necessarily talk about having tests for normality and things like that, but if they're going to be using parametric tests like t-tests and things like that, they need to make it pretty explicit that yes, this is a normally distributed set of data. You're typically going to find that more when you're doing things like randomized controlled trials that has a nice sample size. You're more likely to assume that it's going to be a normally distributed set of data than if you were to, say, have a study with, like, say, 5 patients, right? Because, again, the more people we include, the more likely it is to truly be a normally distributed set of data in a lot of cases there. Okay. Remember that if you're going to be using parametric tests, and going under the assumption that your data is normally distributed, you're going to find that if you use that incorrectly, you're more likely to make type 1 errors. Okay, we'll talk more about that in a few minutes here, but just know that using normally distributed data, or assuming you have normally distributed data and using a parametric test incorrectly, leads to type 1 errors. Now, again, looking at this in non-normal distributions, you're going to find that with the calculations we're going to use on those are typically more conservative in nature, meaning it's harder to find statistically significant differences for those patients. Because, again, in general, you're going to find that you'd rather make a type 2 error than you would a type 1 error. Okay, so using non-normally distributed sets of data, using tests for that non-normal distributed data, which in other words is a non-parametric test, you're going to find you're more likely to find type 2 errors. And again, I'll mention those in just a second there. Also, it's going to be less influenced by the presence of outliers. Usually the presence of outliers are very extreme values. They're typically what makes a data set not normally distributed there. In general, if you're not sure, just go ahead and use or assume you have a non-normal distributed set of data. Use non-parametric tests because you're less likely to make one of those type 1 errors there. Okay. Remember that when you're using a normally distributed set of data, typically you're going to talk about means and standard deviations. When you're using non-normally distributed sets of data, or you're using, say, something like an ordinal variable, you're more likely to use medians and interquartile ranges, and that's a better way to describe the spread of data than you would if you're using a mean and standard deviations, as you would with a, say, normally distributed data set. Now, getting into things like confidence intervals, remember that oftentimes when you're doing comparisons with data, you'll find that they give you a confidence interval as well. And that's really just saying how confident you are that the actual true value, if you were to, say, extrapolate from your data set and apply that to the population as a whole, how confident you are that the true value is somewhere within that range, right? Generally, we try to be 95% confident. That is just kind of the standard we've gone with. It's not perfect because you can still have 5% of the time you could be wrong there. But typically what you find is that narrower is going to be better in terms of confidence intervals, because it gives you a much more narrow range that you're very confident has the true value of what the general population would be. And so as an example, you're going to find that the N, or the population, the sample size you have, is really going to have a big effect on your confidence intervals. Typically, the more people you have participating, or the more values you have, the bigger the N, the narrower the confidence interval is going to be, the smaller the value range you're going to have to say, well, I think the actual true value is somewhere listed here. So what does that really mean? As an example here, I have, say, different studies with different numbers of people here, ranging from 10 people all the way up to 100,000, and I took their average systolic blood pressure. Okay. Now, again, if I have 10 people, and say I were to recruit off of a college campus, I may have some very athletic young people there. They're probably going to skew a little more towards low values there because they're very healthy. Versus, say, if I went to the nursing home and I was taking random people from there, you're going to find they're probably not very representative of the general population. So you may find that would be a non-normally distributed set of data. But let's say we're just going to look at the average blood pressure for these patients here. And you can see if I just did it with 10, I'd have, say, an average systolic blood pressure of 106, and then a 95% confidence interval that ranges pretty greatly, anywhere between, say, 93 all the way to 132. It's a pretty wide range there. But as you get larger and larger sample sizes, say 100, 1,000, 10,000, you'll typically find that you'll get closer and closer to that population true value, because again, you're getting closer and closer to the actual population size, right? And so you should get closer to what the actual true value is going to be there. In addition, you're going to find your confidence interval gets smaller and smaller, because I'm able to say with greater confidence that, hey, look, this value, the true value, is probably somewhere between 117 and 121, right? That's a lot more narrow range, possible true values, than if I was, say, just doing it with 10 patients and I say, well, it's probably between 93 and 132. That's such a big range, it's not clinically all that relevant, versus if I were to say it's between 117 and 121, it's a very narrow range of values. It could be the true one, right? All right, so looking at the difference between parametric and non-parametric tests, remember that with a parametric test, you're going under the assumption that you have a normally distributed set of data. So you either needed to test that by testing for normality, or if you had a really good randomization procedure, you have a large sample size, that usually will help you to be more well assured that, yes, this is probably a normally distributed data set. Remember, the calculations you're using, whether it's a t-test or an ANOVA, make it where it's easier to achieve significance, right? You're more readily able to find statistically significant differences there if they're actually present. But that also means that if you use this incorrectly and you're using it on a non-normally distributed data set, you're more likely to make a type 1 error, meaning that you say that, yes, there's a difference between the groups, but there actually isn't, right? And so again, that's going to be a false positive result. In comparison to that, you have the non-parametric tests, which are going to be doing away with the assumption you have a normally distributed set of data, or you just use it as a default if you don't want to run the normality test yourself. And you're going to find that they make it a little bit harder to achieve significance with those tests because they want to reduce the risk of making a false positive or type 1 error. But on the flip side, you're going to be more likely to make a type 2 error, meaning that you say there's no difference between the groups, but there actually is. And so because of that, that's usually an issue of needing a bigger sample size to show true differences if they do exist there, right? You need more power to avoid making a type 2 error. And to give an example of a parametric versus a non-parametric test, you're going to find that a t-test will be analogous to a Wilcoxon sign rank test, or say an ANOVA is analogous to a Kruskal-Wallis test. And in a later video, we'll show you some of the common data comparisons you'll have to be dealing with. But this is just kind of giving you an idea of what you're looking for. And if you see that they're using a parametric test, see if they even looked for normality, or see if they're a randomized controlled trial. They're using non-parametric tests and they didn't find any results or that were statistically significant. Well, maybe you can look to see, well, maybe it wasn't properly powered. Maybe they needed more patients. They could have found a difference, right? These are things you want to be looking for and when you're analyzing your literature. Anyway, that's it for parametric versus non-parametric statistics. If you have any questions, let me know, and I'll talk to you next time. Thanks a lot. Bye.